So in this, I think today I wanted to tie up some odds and ends related to link mechanisms. You looked at COMSOL's implementation of hydromechanical behavior. We talked a little bit before about EGFAM's implementation. I'd like to kind of revisit that briefly and talk about other ways of solving these equations, both in terms of applying it to dual porosity media. So we made the point that dual porosity media are quite a nice way to talk about fractured porous media that have very different attributes. Fractures being very fast flowing but no storage, and the matrix being very low permeability, slow flowing but with large storage where all the fluid is stored. You can also couple those to be able to look at them as mechanically linked as well, in the same way that we've talked about pore elasticity. And so maybe we'll spend a little bit of time talking about that. We'll talk a little bit about methods of coupling in thermal effects and doing it either implicitly, just by looking at the equations, and talk about that in overview. And then we'll talk about how to link these, maybe using two separate codes. And so maybe you have a code that does solid mechanics, maybe you have a code that does transport processes. They don't talk to each other, but in the same way that we've talked about basically modules that we have to link with the off-diagonal terms in the matrices, how would you link those codes together? What information would you parse between them to be able to make them think that they're solving a couple of problems? So those are the things that I'd like to look at today. Before I do that, though, I wanted to skip back to, I think, this. And so you should always be aware that anytime you want to do anything, if it's not going to, if you don't want to suffer the injustices of presenting something and someone pointing out to something in your presentation that doesn't make sense, then you should always make sure that you validate and verify models. I'm not sure necessarily certification is a big thing for us. I always get the meanings of these. I never can keep the meanings straight in my mind, but they do have very specific meanings between validation and validation, which I tend to use interchangeably. But verification refers to the fact as whether you could check your model against a closed form solution for the appropriate mechanics that you think is in your model. And so in other words, you have a model that, say, has Hooke's law in it to represent linear elasticity, and it has a linear Darcy law in it. And so if you solve a problem with that, there are certainly some analytical solutions available that you could check your model with. And actually they're given here, for instance, for a very simple case of loading on a foundation. It comes from BO's 1941 paper. You put a load on the foundation at time t equals 0 plus, and you look at how the surface layer of this deforms as a function of time. It would look, if you plotted it, something like this. Log time versus deformation would do this. And this asymptote, this would be displacement, uz. And so it'd start off at 0 displacement, you'd add a load, it would squeeze the fluid out of this like squeezing a sponge, and in response to this it would reach some new equilibrium where there are no excess fluid pressures included in here, and it has a new deformation. And it'd be very easy to compare a model, of course, to look at that solution to see that you actually find yourself on that boundary, on that response. And so it's a very important thing to do. Doesn't mean that you need to develop your own codes, but any code that you pick up off the shelf and start using, then verification is something you should do, just to prove to yourself in a simple way, and exercising it in as many ways as you think prudent, is to make sure it's really doing what it's doing. It may well be that it's doing what it's doing, but you've interpreted one of the instructions for a material property in the wrong way. So maybe you're using a thermal coefficient of expansion instead of volumetric coefficient of thermal expansion, which would be a factor of 3 off. And if you don't know that, then you will end up with numbers which are not true to the system you're dealing with. So verification is one important thing in making sure that you are getting the results that you want. The other one is validation, and validation is different. It's not meaning that it's satisfying the equations that are really in the system, but it means that it satisfies reality. And so you could get a solution for the coupled solid mechanics flow process we just talked about, loading an aquifer that perfectly adequately addressed all of the physics that you have in your problem. But if, for instance, in your model, a big part of that compaction, say in lake time, was just due to chemical dissolution at stress contacts within grains, pressure solution, and that it kept on deforming after that, if you didn't have that physics in it, then it wouldn't give you the solution that you'd see in reality if you instrumented a site that was doing it. And so, as I say, I tend to use verification and validation interchangeably, but they do have very specific meanings. Verification is whether it adequately addresses the physics that you put into it, and validation is whether it represents reality, basically. Certification isn't something that we worry too much, but for instance, in the radioactive waste program, the only way that you can figure out whether a nuclear waste repository will be doing what you think it might be doing, that you might like it to do in 1,000,000 years, which is the design scale that's set by EPA for the license application for Yucca Mountain, as it was, is to be able to model it. You can't do it in any other way. And so in modeling it, you hope you have all of the appropriate physical processes involved, and you hope that you are, in a verifiable way, representing those processes in an accurate way. And so all of the codes that were used for things, important things like Yucca Mountain, I presume it's probably the same for codes that you use to design reactor vessels for nuclear reactors as well. The QA, quality assurance and quality control, QA/QC, requires that when you change the code, all the changes that you add in the code are dated in some way and archived at individual points in time, so that you have some absolute record of how these things have changed, and so that there's some I guess transparency in being able to check whether the results that you get to verify these important processes are really what's going on. And then of course you might wonder whether something's going to happen in the system outside modeling, which is, most people think of in terms of how you verify waste repositories. You put the stuff in, you seal it up, it heats up, you get thermal stresses, those give you changes in permeability, you boil off the fluids, etc. And once you allow that process to take its full place, then you can say something about how many canisters would break open and what the output would be from those canisters and what the impact might be at some compliance location 30 kilometers downstream in the groundwater aquifers, and that's fine. But if you don't take account of the fact that, for instance, Yucca Mountain has been volcanically active within the last 10,000 years, and that one of the scenarios that was looked at was that a volcano or a conduit would open up, a diking episode would open up underneath it within the lifetime of the repository. If you don't account for that in your calculations to be able to see whether it would resist intrusion, volcanic intrusion as it was called, then you don't necessarily have a certified solution to your problem that you might be happy with. And so this one page here was just taking care of, I guess, verification, right? Verification as to whether the codes that you might develop through EGFAM or through COMSOL would actually be verified against what's really going on. So important thing in everything we do, that someone can reproduce your work in the papers that you publish. Verification is all to do with that. And sometimes some journals are now calling for codes to be made available as supplementary materials when you publish something, so that someone can actually either use it and check it, etc. That's part of the scientific process in being able to verify those things. Okay, so that was the first part. So I wanted to just quickly go back to look at EGFAM again. We talked a little bit about it in 6.2, but I wanted to just complete it and talk about the bigger picture. You remember that we spent some time in 6.2 talking about what the form of these equations are. We talked in detail about the physical representation of these equations and what they represent. I don't think we've said it, but it's perhaps worthwhile saying it. One way you can think about this, I think a useful way you can think about the physical meaning of these expressions is in the same way that, for instance, you could think about I'm going off topic, but let me do this. If you think about a stiffness matrix, you know that when we solve solid mechanics problems, we write something which is F equals Ku. And I suppose you don't need to use a very sophisticated element to show this, but if we wrote this out in terms of looking at a single element, and we wrote out the stiffness expression as F1 and F2. So in other words, we know that we can define at nodes 1 and 2 either a force or a displacement, and also at node 2 a force or a displacement. Then what we could do is, if we wrote out the stiffness expression, we know what it is. So it's AK over L. You'll remember, right? And it's just a long time since we've done this. 1 minus 1 minus 1, 1, you may recall. And if that's wrong, isn't it? And we relate these displacements, then one way to think about this is in terms of what these individual components mean. And so what you could do is you could think about holding this thing static so that U2 is equal to 0. And if U2 is equal to 0, then you would write this expression as it would be that F1 is equal, I can write this. In other words, if this goes to 0, then these terms here, when you multiply them through, become irrelevant. And physically, what these columns, or this column of the matrix means, is they are the forces F1 and F2, and it would be equal to AK over L, and it would be 1 minus 1. And so immediately we know what the magnitudes of the forces would be. Ignore. And that is that the, I guess it would be 1 and U1. And yeah, I guess that's not the point I was trying to make. If we apply then a unit displacement to this, say plus 1, in other words, we're pulling it up by plus 1, and then in that case, the magnitudes of these terms within the matrix then physically represent the forces that would be applied in this equilibrium system to be able to satisfy that geometry that is, one node is pulled to a magnitude of 1 and everything else is left not moving. Likewise, if you had a element that looked like this, which for instance just had one displacement degree of freedom per node and did exactly the same thing, you hold all these nodes at not moving, all these nodes except for one not moving. You apply a force F1, say equals plus 1. Then the stiffness matrix you get out of this, as you know, is going to just be equal to the column. The first column for this is going to be U1 equals 1, and these other terms will be equal to zeros. And so the forces that would result would be the magnitudes of these 4 terms that exist there. Okay. And so you can think about these stiffness matrices or conductance matrices in terms of these magnitudes. The other thing which also makes sense, or should make sense, if you look at any of the stiffness matrices or flow matrices that we've produced, the other thing that's true is if you add all these terms together, either on the vertical single column or on a horizontal row, they'll all add to 0. And the reason for that is, in this particular case, I think we talked about it when we talked about flow problems. The reason that that's the case if you talk about flux problems is that this means that the volume into the flow rate into the element has to, through one node, has to equal the flow rates out of the elements at all the other nodes. In this particular case, what it's saying is that if the fact that these individual terms in this column all add to 1, it's saying that to satisfy equilibrium, all the forces in a vectoral sense have to add to 1. So if you're pulling up with a magnitude of a force here, which is equal to 1, then to keep it in equilibrium, there has to be a force here, here, and here, such that these three ones I just drawn here have to be the same vectoral magnitude in the y direction as the one that's applying to it. And so that's the physical meaning of these matrices not only being symmetric, but also in terms of the individual terms on the leading diagonal adding to 0 as a requirement. So the reason that I started talking about what happens if you make one of these deformations equal to unity and turn the others off is that you can also do exactly that here. So for instance, you could turn this to being unity, and you could set the pore fluid pressures not to change. And if you do that, then what that physically gives you is a reasonable interpretation of what these now matrices are meaning in terms of process. And so the process would be that if this is unity and this is pressure, obviously these would be deformations within the system. So what we're going to do is we're going to apply deformations to this, and it's going to give us magnitudes of forces that have to be applied to resist those deformations. As the deformations build, through this doesn't change, this is linear. If you double these deformations, then the forces that you have to apply to keep it in equilibrium will also double as well. So if you double the rate of change of displacements, it'll double the rate of change of forces and how they build. But in also doing this, it tells us something about what could happen here. Let's have the pressures kept to be 0 here as well. And if that's the case, so we apply some deformation here, then it means this vector times this gives us some magnitudes of flow rates. And so what it's physically saying is that as you're compressing it, you're squeezing fluid out of it, and the rate at which you squeeze fluid out of it is given in terms of this continuity equation on the bottom, which says something about the rate at which material is removed. I guess if we try, let's see if it does it. I guess this does it. Oh, I didn't want to do that. Oh, it just does it temporarily. Yeah, fine. And so the other thing you could do is you could do the opposite. You could set this equal to 0, and you could set this equal to 1, for instance. And if you did that, then it would only activate these terms here. And so physically what that would say is that into this force matrix, and we said that the units of this have to be newtons per time, right? Newtons per time because of the rate of change here. Then physically what this is meaning is that if you apply a fluid pressure here, then it gives you the magnitude of the body force that that produces that the boundary conditions then have to resist against to stop it from going out of equilibrium. Likewise, if you apply this fluid pressure to this, this is saying that you're not allowing deformation to occur, but you're allowing fluid pressures to change. And so the amount of fluid that would get squeezed out of this, because these would of course have no influence whatsoever, the amount of fluid that would get squeezed out of this is because you have a rigid skeleton. It can't move because the displacements on the boundaries are not changing because of this term here, but the fluid pressure is changing. So in other words, if you drop the fluid pressure, then the fluid will expand, and if it expands, then it has to come outside of this control volume because now the fluid volume is larger than the pore space, and so it has to give you this flux. And so thinking about things in these terms is useful because it allows you to be able to think about those terms. That's what I was looking to do before. Okay. So that's useful to think of things in those terms. You'll recall that we know what these matrices are. We know that this is the stiffness matrix that operates on this. So this could be K mechanical. And without being too pedantic, he says, writing it out anyway. This was the terminology we used last time for Hooke's law and the strain deformation matrices. This is the Darcy law term, which is A transposed dA dV, where these are the derivatives of the shape functions for the flow equation. These are the derivatives of the shape functions for the solid mechanics equation. The magnitudes of this was a storage matrix, B transposed B dV. First order derivative, I think it had porosity and bulk compressibility of the fluid on there. And these terms were brand new terms. They seemed like brand new terms, but they really weren't quite. They looked something like an integral shape function, a matrix which allowed us to map the terms of effective stress. You remember we defined effective stress as total stress is equal to effective stress plus m times pressure. And if we wrote that out in longhand, it was something like, for 2 dimensions, stress in the x direction, stress in the y direction, shear stress, being equal to effective stress in the x and effective stress in the y, and there is no influence, there is no effective stress due to the shear stress. Brain burp right there. And this M matrix, which was 1, 1, 0, it could be alpha's, the BO coefficient could be in there as well, and operating on fluid pressure, which is a scalar. And so you remember that this, and we didn't note it at the time, this is due to the fact that fluid pressures act only on the normal stresses, and so there is no such thing as an effective shear stress. And I suppose the corollary of that is that we talked about the volume changes. So the change in volume was equal to m times the strain vector. And that, if we write it out in longhand, is 1, 0, 0 for the m. And the strain vector is strain in the x direction, strain in the y direction, and shear strain. And it's we didn't make the point at the time, but we did say that if you take a deck of cards and you scoot that deck of cards by adding a shear stress on the top, so it ends up looking like this, then because this volume here is equal to this volume here, there is no volume change due to doing that. And so I did this wrong, didn't I? No one corrected me, but this is 1. And then the volume change is due to how much it shortens this direction, how much it shortens this direction, but if you shear it, there is no volume change, and so there is no volume change that affects this system, and so the pore pressures that come out of this. So there's a certain, if you like, symmetry between this 0 here and this 0 here in terms of what they mean. Shear stresses are only defined as total stresses, they don't exist as effective stresses, and shear stresses cause no volume change, and the two issues are somewhat related. But I digress. This was equal to the A matrix, dV. And we said that we didn't really say that we'd seen anything like this particularly before, but we have. When we looked at groundwater mass transport, you might remember that we had a matrix that looked like the derivatives of the shape functions times the advective velocity times the shape functions, advective velocity, and the derivatives of the shape functions. This was the advective term. it was a term that was equal to the velocity times the rate of change of concentration with length. So this is the advective term. And you know that when now, if you really did look at those, the movie, where we defined it in terms of the behavior that you want to solve COMSOL in, then the solid mechanics equation that we deal with is this one. And so this term that we operate on is a first order term in space, so it's dp dx. So it's not very different from dp dc dx for transport, and multiplied by some coefficient. The coefficient here had been velocity. So that's all that differs. And so this body force term, which is in the same units as this, you can check the units here, what they should be. It has to be, it's a force per unit volume, right? Pressure is newtons per meter squared, and it's per meter. So it's newtons per unit volume. And so these all have to be the same. But this is this first order term. And so it's not surprising then that when we look at these terms here and what the matrix looks like, then it looks exactly the same as the one before. And so bless you. So the sum, I think it's kind of cool, that the fact that there's some symmetry in this. And so this term comes in here, which is also a first derivative term, since it's really being represented here. And if we look back at what that physical term must be in the expression that we have here, it's this. So it's something that's operating on this. And it looks at first blush that it's really a zeroth order term, which is operated on by a time-dependent derivative, right? Something changing with time. But of course, strains, volume strains, are equal to the rate of change of displacement in the x direction with x, plus the rate of change of the displacement in the y direction with y. And so, indeed, although this looks like a constant, which is a zeroth order term, it's a first order term. First order in space because of these two terms here. And so, hopefully it should all make some. Yeah, it's all very rational. I think if you're able to stand back far enough to be able to appreciate the big picture. And so think of these in physical terms. What did I want to do? The only other thing I wanted to talk about, since we talked about how these, if we have these expressions, we have to take these time derivatives and do something with them. And to do that, we just split this time derivative out as basically this is delta u over delta t, which is basically 1 over delta t times delta u, which is this term here. And if we throw that into here and do all the rearranging that we want to be able to keep these things on the right-hand side, but take these things that we know, keep these things on the left-hand side as unknowns, take these things to the load vector, which would go here, which we know, then we end up with something that looks like this. These are the things we know from the previous step. We know all the matrices in the system, and these are the boundary conditions we apply. And we can just solve it as a simple system of equations. I just wanted to mess around with EGFAM just because we can. Again, I know you can't see this. And we kind of ran it last time. Just to make the case that if I make it bigger, I can make this bigger, but it doesn't help you very much, I don't think. Doesn't have a view. I could have checked this before. But what happens if I change the settings on the desktop, then what it does is it never records this. Of course, you could see it here because you're here, but that would be too simple to solve it that way. Can you see that at all? No, not so much. That's fine. You're being honest about it. Is there a way around it? Yeah, there's a way around it. Okay. So rather than run it, which doesn't matter, what I will do is I will do this. Does this get bigger? It does get bigger. Gets smaller as well. But the screen resolution is still pretty big. Don't need the bottom part. You're thinking, this guy is such a wizard. How does he know all this stuff? Alright, so what the hell is he doing? Good God, get to it already. Okay. Is this going to be a PDF file? Are you thinking? Are you going to put it in there? I'm thinking. I'm thinking too much. Yeah, I was trying to make it into a PDF. Maybe. Took it. Okay. Now we're in business. All right. So now we are kind of where I wanted to be. So, oh, I took the wrong file. That's not the file I wanted. This was the file I wanted. All right. Very patient, aren't you? Where is that? Oh, this is it. Hope this is the one I actually want. Yippee! It is. All right. So in terms of the structure of these things, we've made this point before that all of these codes do one thing. You have to supply a stiffness matrix, which is the main kernel of what is different between a flow problem, a transport problem, a solid mechanics problem, or a problem that tries to couple some of these things together. And it all resides in that one, it can be a single subroutine here. And so this is exactly it that we talked about last time in 6.2, but this is the data file that revolves around it. So physically what this is representing is an element that would look those. That is a triangular element. And as we number things from node 1 to 2 to node 3, we keep up with the prescriptions of what we've said before, is that each of these would have degrees of freedom attached to them, and so on, and the same for node number 3 in terms of displacements and pressures. And so in this particular case, the geometry of this we would know. I think the only thing that's different here is that the numbers of degrees of freedom per node quite clearly are 2 displacement degrees of freedom and 1 fluid pressure. So degrees of freedom per node would be this here by definition. Nodes per element is 3, so that's a triangular element. Number of materials in this case, number of space dimensions is just written in terms of x and y. And so, yeah, maybe there's everything else follows from before, in that if you define the element, in this particular case, it's defining an element in terms of nodes. And so if you were to draw out these particular nodes in terms of x and y, then node 1 would be 1, 1. Node 2 would be 2, 1. Node 3 would be 1, 2. And node 4 would be 2, 2. The data we need to define would be things like Young's modulus. We'd need Poisson ratio. We'd need Darcy's law. We need porosity. And we need fluid stiffness. Actually, if you look back at the equations, those are the only things that we need. These are the 5 things that we need, and we'd have to supply those somehow. There's no reason we can't supply more than 5 parameters, but we need to be able to define those. And this, of course, in MATLAB is just the comment that goes with it. So deformation modulus is 20. So no, the element number is 25. Deformation modulus is 100. Poisson ratio is 0. Permeability is 1. Porosity is 0. And fluid stiffness is 1. Element data. Element number 1 is material number 1, but nodes 1, 2, and 3. So, element number 2 is also material number 1, but nodes 2, 4, and 3. So 2 triangles. And then the only other thing which I guess is specific for this, is how to define what the boundary conditions are. And so conceivably, and I can't remember, but let's presume that this is probably the case, if we're living true to our ideal of wanting to solve a solid mechanics problem for which we know a solution, it might be something where we apply a surface load and we allow this surface to deform as a function of time with the bottom held from moving, in which case our geometry for this, conforming to this particular mesh, very simple mesh, wouldn't give a very good result, would be this. And I'm presuming that's the case. Let's go through that and see if this is the case. This is 1, 2, 3, and 4. And so presumably if that's the case, then what we would be doing is we'd be providing 0 displacements here and an initial pressure. And that would be, remember, we defined it in terms of what are the constraints that we apply, and then what are the magnitudes of those constraints. So if we wanted to apply a force, what would they be? So the force here, if this is unit length, and we wanted to apply, say, this being equal to 1 MPa over a meter, then I suppose this would be equal to half of that, right? So when you add these two together, so 1 MPa times 1 meter times 1 meter is 1 meganewton, and so it would be something like 500 times 10 to the 3. So 0.5 times 10 to the 6 newtons. And likewise, this would be the same. And so there'd be a finite number here. And it would be a load. There'd be a displacement of u equals 0 here in the y direction, and probably also in the x direction for both of these on the bottom, and no defined force. And I don't want to go to a meeting now because I'm having too much fun here. And this would be a fluid pressure. So in other words, we'd want the fluid pressure here to be equal to, held equal to 0, which would be a drainage condition on this boundary. And the magnitude, depending on how we do it here, it would also maybe undefined. So in other words, a better solution would be that Qx is equal to 0. So remember, so for deformation, we can provide for the solid mechanics part a force or a deformation. For the fluid mechanics part, we can provide either a flux or a pressure. And so we can't apply both. So for any of these, all of these nodes are on the boundary, so they will either have a force or a displacement applied. So here there's a force applied but no displacement. Displacement is solved for. Here a displacement is applied and a force would be solved for. And likewise here a pressure would be applied and a flow rate could be calculated because you'll be squeezing fluid out of the top. And here a flow rate will be prescribed and a fluid pressure will be calculated, right? You always calculate the converse behavior. And so how does that work out? Hopefully that works out to be the truth here. So remember that 1 means something is fixed. And so let's just write this out. F equals Ku, or Q equals Kp. In other words, displacements and pressures are similar to each other in this terminology, and forces and fluxes are similar to each other. So this is saying that at node 1, this would be all the values above. This would be displacement in x, this would be displacement in y, and this is pore fluid pressure, or the flux condition. So node 1, we fix displacements in x and y. So this is truly fixed here, so this isn't going anywhere. And I suppose the usual sign for that would be a little thing here which is attached to a triangle. Node number 2, x is free to move but y is not. So this would be what is often drawn as a rollered condition. So in other words, this can scoot to your right, but it can't go downwards. And so that would be what that is. And the fluid pressure is not defined. So if the fluid pressure is not defined and it's a boundary, then the flux is defined as 0. And so this means the flux, since it's this term here, and this is also flux. And for the top ones, no displacement is prescribed, so by definition a force is prescribed. That force could be 0 if it's an interior boundary, but it doesn't need to be 0, it can be a number. So this is, a force is prescribed, and if you look here, the force in the minus y direction, if we wanted this to be, this could be 0.5 E6, right? Just looking at this number here, if we wanted to do that. So that's what these do. So forces are prescribed by the mere fact that these are zeros. So it's not a displacement, but it's a free condition, a fixed condition, a force condition. And likewise for this, yeah, we're setting the flux equal to 0 on the top. Actually, Okay, so this condition that is also set here so that this flux is equal to 0 by this, right? This is defining a force similar to a flux, in other words, because of this, and therefore it's allowing fluid to go out. If we wanted to, we could make this 1, and we could make this 1, and these then would be pressures, P equals 0 on the top, and these terms here would be Q equals 0 on the bottom. And if we did that, then physically what would happen when you load it? You could imagine when you load something and you looked at what would happen. So it's no displacement on the boundary, no flow out of the boundary, a stress being applied on the top. What would happen to the magnitudes of the fluid pressures with depth? Well, ignore first the part that if the water table is here, then the fluid pressure going down here would be hydrostatic, right? Rho GH. So we're only interested in changes because that would be the initial condition. So what we're doing is that we're going to load this. Immediately when we load it, what's going to happen? It's going to try and drain the fluid out of it. It can't. Think of a sponge, a very compressible sponge. You load it. If the sponge is in a membrane that the fluid can't escape, then it'll carry your load and the fluid pressure in the sponge will go out. If the sponge happens to be very low permeability, so the fluid can't get out, then it's going to do the same thing. The pressure will go up. So the initial pressure would look something like this. If you apply a load, you'd find out that the pressure would jump to this magnitude here. This would be equal to 1 MPa. It would be exactly the same as in the calculation, the verification example. Maybe we'll go back to at the end of this. And what would happen with time? This is open, so the fluid can go out of here, but the fluid can't go out of here. So by definition, physically, it would look like this would be time equals 0 plus. This would be T1. This would be T2. You keep on going down here like this. This would be T3. This would be T4. And this would be T infinity, when there's no pressure left. It's back to the original condition. And so I haven't drawn it very well, but you can imagine that this has to be a right angle here, right? And it has to be a right angle here because we know that by definition, fluid velocity is equal to permeability, viscosity, change in pressure with location. And so, in other words, if the pressure gradient is finite, then there'll be a velocity. The only way that we can get it so that there's no velocity across this boundary is if you think of this as a mirror, it's how you do it in finite differences. We don't use those finite differences here, is you have a reflected boundary, right? In finite differences, often you could think of this being symmetrically a mirror image of this below as it is above. If that's the case, then this has to be perpendicular to the boundary. And if that's the case, then the hydraulic gradient across here by definition is 0. If the hydraulic gradient is 0, because you have this mirror condition, this mirror node on the other side, then there is no flow that goes across here. And therefore, as a function of this being perpendicular to the boundary, there is no velocity, and you've satisfied your no-flow condition. And so we'd expect that to be the case. Okay, very good. Yeah, and so that's it. And so if you want to, you could use EGFAM to be able to solve it. But that's basically the expression that we're trying to deal with. I made reference in this to a particular location, and I guess the particular location is that 3. Gone too far. Is this little verification example which exists just before this here. So in other words, if you look at Bio's paper, which is this is just drawn from, This is BO 1941, I think. Not even I was born then. I know you weren't. Then this is just a solution for that particular loading of applying something on the surface, and you could follow the deformations that occur just by using the appropriate boundary conditions. That's it. So it's useful to be able to get a feel for what these are. We talked to verification and validation, and so you should be able to do that. The other thing that you could do, so switching gears away from looking at the computer, you probably can't hear it. It's working very hard for some reason over here. The other thing that we could do, and maybe I'll just spend a little bit of time kind of introducing the basic idea of it, is that we made the point that dual porosity, dual permeability systems are quite useful systems to represent real life because of the fact the fractures represent fast fluid pathways but react very quickly because they have no storage, and all of the goodies, water if you want to produce it for agriculture, or oil if you want to produce it as a fuel, exist in the pore space. And so we know how to do that for flow problems, but you could also imagine introducing that to be able to look at consolidating dual porosity media. And the approach to do that is relatively straightforward, and really you end up with a system of equations that are very similar to the ones that we had before. And it revolves around the fact that we said that we could represent this system by two overlapping continua, one representing the porous medium, one representing the fractures. And as an artifact of that situation, it means that we had a fluid pressure. Of course, we only have fluid pressures within the system, but sometimes those fluid pressures would be in the fractures, P2, and sometimes they would be within the matrix, P1, even though you can only really define a fluid pressure. So what we could do is we could define Terzaghi's law of effective stress in terms of the total stress which is applied on the system. Remember, we write the equilibrium equations in terms of total stresses, but deformation and failure is written in terms of effective stresses. And so we need to use this for Hooke's law. And so we could write it in terms of an effective stress law for the total stresses in the porous medium, the effective stresses, and the fluid pressures. And all of these other relationships will look familiar. And also do exactly the same for the porous medium as well, where we have the same variables. We know that from equilibrium that the stresses that are applied in the porous medium and the fractures must be the same because we're thinking of them as in series. So in other words, if we think of the porous medium here, and say we think of all the fractures above it here, and we apply a stress vertically down and up through this, then by definition, by equilibrium, the stress in this has to be the same as the stress in this. And so we can suggest that the equilibrium, which is defined in terms of total stresses, has to satisfy this. We could write Hooke's law in terms of some appropriate stiffness relationship for, if this is for the porous, and this is for the fractured system, then we could write them in terms of appropriate terms that go into here, which we can get. And then if we do that, we can invert these. So in other words, if we multiply this by d minus 1 and d minus 1, or d1 minus 1, then this term is here. This is what we're calling a compliance matrix. And the product of these two is just the identity matrix. So we're just inverting this to get strains as a function of stresses instead of stresses as a function of strains. That's all we've done. And if we do that, we could define the total strains as the sum of the compaction that occurs in the matrix plus the compaction that occurs within the fractures. And if we do that, then we could take this, write this equation in terms of d sigma 1, right? We could substitute it into here, and when we could substitute that into here. Likewise, we could write this equation in terms of d sigma 2 prime. We could then substitute that into here, and then we could substitute this into here. And we end up then with a very kind of complicated matrix equation, which is this. But then these are the total stresses, which remember we want to solve our system of equations in. If we can now rearrange this equation so that it defines it in terms of this total stress, with all the other terms on the right-hand side, then we get equation 6, which is what we want. So before, what we had for single porosity, we had the fact that the total stress is equal to the effective stress plus a change in fluid pressure. That was basically our statement of Terzaghi's law. If we do it for the dual porosity system, we still have total stress, which is what we're going to write our equilibrium equation in, but now it's defined in terms of the fluid pressures, not just in one medium, but in the fractures and the pores, and also in terms of the deformation of the solid medium, the composite medium. And if we substitute this statement of the constitutive equation in terms of total stresses into the equilibrium equation, last time I think we used A transposed prime. This is the derivatives of the shape functions, and then we have an equilibrium equation, and then we do the rest of the substitution. And if we do that, then we end up with a system of equations which are written in terms of this three-part relationship. So you remember before, when we talked about dual porosity media, we had a fluid pressure in the matrix and a fluid pressure in the fracture. We had terms which were represented here, and we had permeabilities in the matrix and the fracture, no deformation part. Let's see if this will erase. It does. When we talked about single porosity poroelasticity, we had these terms here. We had deformations and fluid pressures. They only operated on these terms. And this was the stiffness matrix. This is the storage term, just due to expansion of the fluids in the pore space. And these cross-coupling terms were these symmetric terms. They were the transpose of each other. One says how much body force is applied if you put a fluid pressure in there. The other one says how much fluid is squeezed out if you deform it by some amount. They were equivalent. And so now all we've done is to put this together in some way to be able to now look at all three, and then you can figure out for yourself exactly what these different coupling terms mean in terms of their physical representation. So it gets complicated, and that's why I'm not necessarily rushing it, but I don't think it's super important to know, other than the fact that you can do all kinds of manipulations of physical systems that it's useful to understand a little bit about. I don't think you necessarily have to understand everything about all of these systems, but it's interesting, I think, in a physical sense, to be able to get a feel for what we're attempting to do in all of these cases. And you could solve it implicitly by doing that. The other thing which I said we would do when we entered into this was that we'd talk about coupling. I've gone much too far back now. I think that's close to where I wanted to be. I'm just looking for the title slide for what we're talking about today. Is that in the same way that in looking at these dual porosity systems with mechanics added, which is really what this was, you can also think about putting these systems together when you add, for instance, thermal effects. And so let's talk about that in a broad, brushed way of describing it in terms of what COMSOL, for instance, would do. And if you looked at the stuff in 6.3, you'd have seen, hopefully, that what COMSOL does is it takes, for instance, for hydromechanical problems, it takes the solid mechanics part, and attempts to solve that in terms of the boundary conditions. And if you want to couple it to the fluid flow part, where these are the individual governing partial differential equations, what it does is it makes you put in a body force that accounts for the forces in the x direction and the y direction as a function of the fluid pressures. The magnitudes of those, we know what those matrix relationships look like if we're solving it in EGFAM, but that's not really the way that this high-level language of COMSOL wants that information. And so what it ends up with this is that within the element, it would want a magnitude of an equivalent body force in the x direction, and it would want a magnitude of the equivalent body force in the y direction. That's how it deals with this term. That's how it deals with all of these terms, right? We've said that we have to add apples to apples. And by definition, if you look at the units of these, we already said a few moments ago, it's newtons per unit volume, newtons per meter cubed. Actually, it's not. It's yes, it is. Yeah, in this one, it's newtons. So pressures is newtons per meter squared. Per meter is meters cubed. And this coefficient here is the BO coefficient, which has no units. And so in COMSOL, the appropriate equation would be something like some term, alpha BO, and it would be multiplied by something which would be px. And px is a term that represents dp dx. And so somewhere within the architecture of COMSOL, it's calculated this magnitude. You can look it up in the, you used to be able to look it up in the equation sheet, and it would be that px is equal to the derivative of pressure measured at the Gauss points. And this would be something like alpha b times, not surprisingly, py. The term that represents this would be a term that represents the same thing. It's a body force due to thermal expansion. The units of thermal expansion are, so thermal expansion of rocks is something like 10 to the minus 5 meters per meter per degree C. So these are strains, approximate magnitude. So it has units of 1 over degree C. And so in this particular case, actually it's not going to be the right magnitude, as it has to be apples to apples. And so it's not quite going to, yeah, okay. That's what this is. This has to be multiplied through by modulus in some way. That would then give us, yeah. So modulus ends up going into this. This is also multiplied through by, say, modulus. And so the units of this are going to be newtons per meter squared per degree C. If you divide through by another meter, then it's newtons per volume per degree C, plus the derivative of temperature on the top, which knocks out degree C. So it's the same units. So in this particular case, it would be equal to an additional amount, which would be alpha T times, and it could be Tx if it does it, or also COMSOL has this command where it can take a derivative of something of T with respect to a coordinate dimension. And again, not in terms of a partial, but T with respect to the y coordinate direction. And that would give you the components that go into this. This is the inertial term, we don't care about that. But you can work out the units. The units of this inertial term have to be a body force as well, because this whole equation is basically representing this. F equals ma. Appropriately scaled, so it's per unit volume. So it's force per unit volume, not just force. Okay? So the units of this have to be consistent as well. If you look at the fluid flow terms, then they would have to be similarly represented. And so you could imagine the expressions that would go into that. And this would be, in COMSOL, the displacement gradients would be, I think, U is equal to displacement in the x direction, and V is the displacement in the y. And so by definition, similar to this, Ux would be the same as epsilon x, and Vy would be the same as epsilon y. And so this term here would be something like alpha B times, these are strains, these are volume strains, and so it would be something like the derivative, differentiate the strain in the x direction, Ux with respect to time. So this would be epsilon x dot. And adding to that the derivative, which would be something like Vy, the strain in the y direction, differentiated also with respect to t, close brackets. And so this would be the effect of how much fluid gets squeezed out of the system by applying deformation to it. You squeeze the sponge. And so those are all things that we talked about in terms of hydromechanical coupling. But now we said, well, we want to make life even more interesting for ourselves by adding thermal flow into the system. So the equation that represents thermal flow is this. It's missing one term. These again have to be apples and apples. And so how would we represent some of those components in these other equations? So what else do we have to account for in the fluid flow part? So you could imagine that if you take a block of porous medium and you fill it with fluid, and you take a beaker, you fill it with sand, you put water in it, and you heat up that water. What's going to happen to the water? It'll expand. And so you can imagine that some amount of fluid is going to come out of the sand and it would overflow the beaker. So that is one physical mechanism that's saying the pressure's not changing in the sand, the displacement or strain isn't changing in the sand, it's still a beaker that's sitting there, but the temperature's changing and it's allowing it to expand. And so since the fluid flow equation is written in terms of if you change the fluid pressure or if you change the strain, some things happen. You squeeze it out by changing the strain. If you keep the porous medium rigid and you change the fluid pressure, if you drop the fluid pressure, the fluid expands and it overflows. That's what this term is. What happens if you keep the pressure and strain both zero, constant, or constant, it's changes, right, we're interested in, but you heat it up. If you heat it up, it expands. And so this term here would be, by definition, the change in volume of the fluid as it changes temperature. And so how much fluid is produced as you change the temperature over some increment of time. And it would be the same as before. This would be the coefficient of thermal expansion. So I could imagine that it would be, the term here would be something like coefficient of thermal expansion of the fluid times, I think it would be the porosity, right? Because it's only in the pore space, and multiplied by dt dt. And so in COMSOL speak, this would be something like a flux. So these are equivalent fluxes. And this would be equal to alpha fluid, alpha F, multiplied by porosity, multiplied by something like the derivative of temperature with time. And it would, so you don't need to know what the commands are for COMSOL, but it's maybe useful to get an appreciation for these. And the one take-home message, I think, is that because these equations are all written in terms of the same units and they physically mean something, this is a flux. So this is basically stop it. This is a volume flux per unit volume. I think of the units of this. So this is a strain times a constant. So this is a volume per time. So this is meter cubed per time. And so the units of this are volume. So it's per unit volume of your aquifer. So these just have to satisfy this. So if you look at this, and I haven't brought, we won't do it, there's an extra term that you'd have to add into this. So if you wanted to have thermal flow, you could think about what isn't accommodated in this equation when you talk about conserving the appropriate components. You have something that represents temperature here. So this is the conductive flux. This is the advective flux, which is driven by fluid pressures, so it's satisfying this. This is the thermal inertia. But the one thing that isn't included in this is what happens if you have a hot sponge with hot water in it. You don't change the fluid pressure, you don't change the temperature, but you physically squeeze the sponge with deformation. And so the deformation that comes in here. So in other words, you can imagine that there would be a term in here that would say something like the change in strain with time. This is a volume per unit time, in other words this. And you have to apply some amount of thermal energy to that. And the thermal energy would be something like the density of the fluid, the specific heat capacity, and whatever the temperature of that fluid is. So this would be the amount of thermal energy you lose, and you'd lose it by squeezing out a mass flux. So this would be a mass flux, which, well, that's right. This would be a Q multiplied by a density, which is equal to a mass flux per unit time. So that's what this term is here. This is a mass flux times how much the specific heat capacity and what its temperature is. So this is a mass flux, and this is how much energy it has per unit mass. And so mass flux goes out, this energy per unit mass, that's how much energy you lose by squeezing stuff out of the sponge as a function of compaction. And so I think it's interesting to look at all these things in terms of what they mean in a physical sense, and we'll leave it there. Exciting stuff, don't you think?